Hello and good morning, students. Welcome to Vista's e-learning and online educational platform. My name is Denzil, your physics tutor for class 11. Let's get started with today's session. Today, we discuss one of the most important conservational laws, which is conservation of momentum. This is a session 4 of the chapter Laws of Motion. Now, there's one such conservational law which you might have learnt in lower standards, which is conservation of energy, where it stated that energy cannot be created nor be destroyed, but it can only be transformed from one energy form to another. So in this case, we will discuss the same conservational rule, but for a momentum. So let's take a look at this by a given example, which is firing of a bullet. Now, when a bullet is fired from a pistol, like you observe in this video here, what you observe is when the bullet is fired, the person holding the gun experiences what is called as a recoil. The recoil of a pistol. Now let us say that the force by a bullet, which is given by FB, and the force of a gun given by FG, the two are related by one another by Newton's third law, where it states that for every action there's an equal and opposite reaction. And this action and reaction pair occurs for two different objects or two different bodies. So the two different bodies where action and reaction occur are the bullet and the gun. So let's make a quick note of it. By Newton's third law, Fg is equals to minus of Fb. Now, when multiplied by delta t on both the sides gives you the impulse, my Fb delta t. By multiplying delta t on both the sides gives you the impulse for a recoil of a gun and the impulse of a bullet. And what is an impulse? It's a large quantity of force acting on an object for a very short time. So this impulse is also defined as the change in momentum. So this particular section is change in momentum along the for a gun, and this section is the change in momentum for a bullet. Change in momentum for a gun, change in momentum for a bullet. And by transposing this minus delta P to the other side, you get delta Pg plus delta Pb, which is equals to 0. The sum of the two change in momentum occurring for a gun and for a bullet is equals to 0. So this is what we call as a conservation of a momentum for a given example, firing of a bullet. So the total momentum of an isolated system interacting particle is conserved even for the case where a bullet is being fired. Here's the bullet that is being fired. By taking the set of data, which is this delta Pg plus delta Pb, which is equals to 0, the change in momentum of a gun is final momentum minus the initial momentum. Pf is the final momentum minus the initial momentum. The initial momentum of the gun when before firing the bullet, before pulling the trigger, we observe that the gun is at rest and also the bullet is within the barrel stationary. But only after pulling the trigger, what happens? The bullet is set into motion and the pistol experiences a recoil. So the initial momentum will be 0 for both the cases, for a bullet as well as for a pistol. But the final momentum is not equals to 0. So Pi is 0, Pf, let's call it Pg minus 0. Similarly, for a bullet, same, where you have P of B minus 0. Now when put together in this particular expression, when put together, you get Pg plus Pb equals to 0. Momentum. In the previous session in Newton's second law, describing for a Newton's second law, we defined momentum as a product of mass and velocity. Momentum of the gun is the mass of the pistol and the velocity of that recoil. So mass of the pistol, velocity of the recoil of a pistol, plus momentum of the bullet is mass of the bullet times the velocity of the bullet. Mass of bullet times the velocity of bullet, which is equals to 0. This is how the two are conserved for a bullet as well as for a pistol. If so is the case for a pistol for a bullet that is fired from a pistol, what about two objects which are colliding with each other? With an example of two balls, billiard balls, they come, they collide, and they move away. So collision before and collision after. What would be the momentum? Will the momentum be conserved in this following case? Let us do that analysis and let us observe. First, mass of the object 1 is m1, mass of the object 2 is m2. Initial velocity of m1 is v1i, initial velocity of m2 is v2i. Final velocity of m1 is v1f and final velocity of m2 is v2f, as you observe. Now, what you observe here is that the mass does not change before and after the collision. Mass remains the same, but what about the velocity? The velocity changes. So let's make a quick note of that. Before collision, what will be the momentum? So before collision, we have m1 v1i plus m2 v2i, which is equals to 0. By the law of conservation, what we had learnt in earlier section. Similarly, after collision, we have m1, sorry, let's take that. m1 v1f plus m2 v2f is equals to 0. Since the two are already conserved before and after collision, which means you can put together in one simple format as momentum before collision equals to momentum after collision. And what do we know about momentum before collision? Is m1 v1i, m2 v2i is equals to m1 v1f, m2 v2f. Since the two momentum are conserved before and after, we can therefore imply that the linear momentum is conserved. There is no extra momentum added or removed before and after collision. Therefore, we say that the given momentum, linear momentum, meaning momentum along a straight path, is conserved. Okay, now let's look into few examples of these momentum and how they're conserved. One is hitting of a billiard ball. Each billiard ball weighs about 0.1 kg. When one billiard ball smashes the other billiard ball, which is at rest, and then it moves once it gets hit, there's a transfer in the momentum, but the momentum is not lost nor it is added there. But the total momentum within this system is conserved. Another example of an inelastic collision of two objects of mass 3 kg and 4 kg block, moving at two different velocities, and they start moving at a same velocity. Even in this following case, momentum is conserved. Dropping of a basketball and a tennis ball, where tennis ball is placed above the basketball, you see that the momentum is conserved in the system, though the tennis ball shoots up like a rocket. So you can prove that this given momentum is conserved for this system. And finally, a toy which is called a Newton's Cradle. You must have seen or you must have played with them. So this toy looks something like this. So in this case, it's used in order to explain the conservation of momentum in a given system. Right. Now that we have learned conservation of momentum, we enter into a next section which is called equilibrium of a particle. Particle appears to remain stationary though there are multiple forces that are acting on a particle. An example is a box which is placed at the center. Two persons on either end push the box at equal forces. Though there are equal forces acting on the box, but on the opposite direction, the box remains stationary. It does not move. So why doesn't this box move? Because it has attained what is called as an equilibrium. Here are a few other equilibrium examples. Is this Krishna's butterball, which is located at Mahabalipuram. This rock, a huge, gigantic rock, is stationary. The reason why it does not topple is because the forces that are currently acting on this all cancel out, and therefore it remains at rest. Unless there's a different force which is acting on a different direction, which has to be a greater amount of force in order for it to topple. Here's another example of an unusual bridge which is called a Lucky Knot Bridge located in China. But look at the engineering that has gone into constructing this bridge. Bridges that you are aware of are more typically horizontally laid bridge, but this one is designed. Why doesn't the bridge fall? Because the engineers have made sure that the forces, the total net forces acting on the bridge must result to zero or almost zero. In that way, the bridge does not collapse, rather it remains at rest. So, how can we show that the given forces cancel out? Here's an example of two forces which are acting on the opposite direction. Okay, one inside towards the right hand side, the other towards the left hand side. F1 and F2 are two forces, but since the two forces are acting on the opposite direction, these two forces, when taken the sum of each, will result to zero. So it's as though an object which is placed in between will experience no force. Where else have you noticed this type of forces that cancel out? Tug of war. In a tug of war, you have two teams that pull the rope on the either end. So you have one team that pull the rope on this end, the other team in the opposite end. When the two teams pull the rope with equal amount of forces, what you observe is that the rope remains stationary. The next time when you observe a tug of war competition, why don't you go in between, stand in between, and then try to push the rope. Just slightly push the rope at the center. You will see that the rope will actually sag. Though the rope have been stretched, when you push at the center, the rope will slightly sag. Sometimes you could also say when a butterfly, when it comes and sits, when teams are pulling on either end, a butterfly when it sits, there's a slight sag in the rope, or the rope slightly goes down. So similarly, you have another force here, concurrent forces. When I use the word concurrent forces, forces which are acting particularly at the center or originating from the center, okay? Forces that are from at the center. Now, you have one force acting along this direction, another force this direction, which gives you a resultant force which is constructed by this parallelogram, and you draw. That would be the resultant force of the two. This resultant force is cancelled by the opposing force F3. Therefore, the net force for this system will be also equals to 0. And so is the case in this as well. One force along this direction, the other force in this direction. The resultant force will be along this direction, but since F3 is acting along the opposite direction, cancels to give you a net force which is equals to 0. And therefore, the object remains stationary at rest. Quick question. So this question is based on momentum, conservation of momentum. So let's read the question and try to answer this. A bullet of mass 20 grams is horizontally fired with a velocity of 150 meters per second from a pistol of mass 2 kg. What is the recoil velocity of the pistol? First, let us make note of the things that are given to us. What is given? Given that the mass of the bullet is 20 grams. Good. Velocity of the bullet is 150 meters per second. Good. Mass of the gun or the pistol, which is equals to 2 kg. Excellent. What will be the recoil velocity of the pistol? To answer the recoil velocity of the pistol, let's take the same case what we learned as a conservational rule, that before momentum and the after momentum are two equal. So momentum before firing of a bullet is equals to momentum, should be equals to momentum after firing of a bullet. Now, before firing the bullet, the gun is stationary, the bullet is stationary within the barrel, so which means the momentum will be equals to 0. But after firing, the momentum, after firing, momentum will be mass of bullet, velocity of bullet plus mass of pistol, velocity of a pistol. See? Do we have all the parameters that are needed to find VP? Yes. We know what is mass of bullet, velocity of bullet, and the mass of pistol. But there's a slight problem here. What is the problem? Is that mass of the bullet is given in grams and the mass of the pistol is given in kg. Two different units. So we have to change it to the same unit. So let's convert this grams to kg. 20 by 1000 of a kg. See, we have converted it to kg. Next, substitute to find VP. Mass of bullet 20 by 1000, velocity of bullet 150, mass of pistol to velocity of piston. 0, 0, 0, 0, 2, 15 times 30, 30 by 10 plus 2 times Vp, which is equals to 0, because it is equals to 0. 0, 0 cancels, and then you get Vp, which is equals to minus 3 by 2 meter per second, or Vp, which is equals to minus 1.5 meter per second. Negative 1.5. Why the negative sign? If the bullet is assumed to be moving along a forward direction, which is positive axis, then the recoil will be along the negative axis. Therefore, this will be the recoil speed of that piston, negative 1.5 meter per second. So I hope I've made this clear, right? Or that's the bullet that's been fired. So to show you, bullet that moves along forward direction and the recoil is in the opposite direction. So that is all I have for today. Thank you for joining me. And the next session, we will discuss concepts that are more related to opposing forces. And these opposing forces, we will soon discuss them. So until then, everyone, take care and have a nice day. Bye-bye.